Let us now discuss Fourier series. Fourier series is a mathematical tool used to represent periodic function as sum of simple sine and cosine functions. Fourier series has a very wide application in advanced structure mechanics. Fourier series help to represent the applied loads, stresses, and strains in terms of sine and cosine function. And because of their high rate of convergence, they are very popularly used in advanced structure mechanics. In the case of Fourier series, we have got an unknown function which is represented as a sum of cosines and sine function. Each term of cosine and sine function is multiplied by a weighting factor. So we can see that the cosine function is multiplied by the weighting factor an, and the sine function is multiplied by the weighting factor bn. In addition to sine and cosine functions, we have another constant a naught, which is called the baseline constant. Together, we have on the right hand side a naught plus a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x plus a3 cos 3x plus b3 sin 3x, and so on and so forth. So all the trigonometric terms have been shrunk into this compact form of an cos nx plus bn sin nx, and we are saying that n is ranging from 1 till infinity. As we said that the Fourier series is used to represent any periodic function as the sum of sine and cosine function. So a periodic function is that function which repeats itself after equal intervals. As we can see in this figure, we have got this function which is repeated after equal intervals. So this type of function can be very easily represented by Fourier series. Or in structure mechanics, we have got loads, stresses, strains, etc., which can easily be drawn into a Fourier series. The coefficients a n and bn can be found as equal to 1 by pi integral minus pi till plus pi f of x times cos nx dx, and the term f of x cos nx dx is inside the integral. Similarly, bn is equal to 1 by pi times integral ranging from minus pi till plus pi and having f of x sin nx dx inside in the integral. We will see in a minute how these weighting factors are derived. The baseline constant a naught is equal to 1 by 2 pi minus pi till plus pi f of x dx. So this baseline constant is actually the average value of a function. So in reality, we are trying to approximate any function into a series of sines and cosines. Just to remind ourselves, cos x has got a shape which looks like this one. This is a full cycle of a cosine x. In the case of cos 2x, we have two cycles of cosine x within the period 0 till 2 pi. Similarly, cos 3x has got three cycles of the function within the period 0 till 2 pi. In the same manner, sin x is a sine wave between 0 till 2 pi. Sin 2x will have two sine waves within the period 0 till 2 pi, and sin 3x will have three sine waves within the period 0 till 2 pi. So we are approximating our unknown function by a series of these sines and cosine functions. In addition to that, we have a baseline constant which will be an average value of a function. So this function, which is periodic, will be made equal to the average value of this function plus series of cosine and sine waves shown over here. These weighting factors will tell us how much proportion of these trigonometric function will contribute towards this unknown function. So from this, one advantage of Fourier series can clearly be seen. Fourier series can tell us how many frequencies the unknown function is made up of and which are the governing frequencies. So for example, if we have got an unknown function whose a2 is very high as compared to other weighting factors, that means that the contribution of cos 2x is very high, and hence the pi frequency will be the dominant frequency of that function. Please note that all these functions have got periods 2 pi. Thus, their frequency will be equal to 1 by period, which means 1 by 2 pi cycles per second. Now, let us try to understand how these coefficients are derived. Before discussing the derivation of these coefficients, it is important to appreciate that there are some orthogonal trigonometric functions which are zero. So, for example, if we have a trigonometric function cos nx and cos mx, and we integrate this function between minus pi and plus pi, we will always get 0, and we can prove it by opening this, as long as n is not equal to m. Similarly, if we have sine nx and sine mx dx, and we integrate this function between minus pi and plus pi with n not equal to m, we will always get 0. Sine nx cos mx integrated between minus pi till pi and having n either equal to or not equal to m will give us 0. In a similar manner, we have sine mt dt between 0 and 2 pi will give us 0, where m is any integer. Please note that in all these identities, our period is between 0 to 2 pi. So if we take 0 to 2 pi, or if we take minus pi till plus pi, the overall period comes out to be 2 pi. So it really doesn't matter how we are trying to integrate it. The important thing is that we should integrate it between 0 to 2 pi. The reason that this limit doesn't matter is that we have got a periodic function which is repeating itself after equal intervals. In the case of Fourier series, it is important to appreciate that the trigonometric functions which are making up the Fourier series have got a period between 0 and 2 pi. So all the functions which are involved in the Fourier series, they have got a period between 0 and 2 pi. Therefore, all these trigonometric functions make up what's called a trigonometric system. Although individually this function, for example, has got a period of pi, but in the case of Fourier series, we consider this function between 0 and 2 pi. So the period of all these functions is taken as 2 pi. Sine and cosine functions considered in the Fourier series have the period 2 pi. It is because of this reason that these orthogonality integrals are taken between minus pi and plus pi, or between 0 and 2 pi. We'll now try to derive the first term of the Fourier series. So we have got this Fourier series. Let us integrate this Fourier series between 0 and 2 pi, or between minus pi and plus pi. So left and right hand side are integrated between minus pi and plus pi. So we have f of x dx minus pi plus pi on the left hand side equal to a naught dx minus pi plus minus pi till plus pi integral an cos nx plus bn sin nx times dx, where the n is ranging from 1 till infinity. Now, according to the identities we discussed, the cos nx and sin nx minus pi to plus pi dx is equal to 0, as is shown over here. Thus, that will give us the value of a naught equal to 1 by 2 pi minus pi to plus pi f of x dx. And that is why we call our a naught as a weighted average. So this is taking average of our function. Similarly, we can find the other coefficients. In order to find an, we multiply both sides by cos nx. So f of x is multiplied by cos nx, a naught is multiplied by cos nx, and this whole term consisting of cos nx and sin nx are also multiplied by cos nx. Then we integrate that between minus pi and plus pi dx, the same thing we did over here. And using the identities we define over here, we get the value of an equal to 1 by pi minus pi till plus pi f of x times cos nx dx. Similarly, in the case of the third term, which is bn, we can multiply both sides by sin nx and use the same identities over here and get our bn equal to 1 by pi integral minus pi till plus pi f of x times sin nx dx. So far, we have discussed the Fourier series corresponding to period minus pi till plus pi. However, it is possible that our period is of some other value than pi. Like, for example, if we have a period between 0 till 2L, then how can we work out our Fourier series? Especially in the case of applied loads, we can have a period in terms of some other value than pi. So let us now try to discuss how to write the Fourier series for an arbitrary period. For an arbitrary period, we can write the Fourier series equal to a naught plus summation of n is equal to 1 till infinity, small bracket, an cos n pi x over L plus bn times sine n pi x over L, where a naught is 1 by 2L minus L till plus L f of x dx. An is equal to 1 by L minus L till plus L. Limit of the integration, where inside the integral we have f of x times cos n pi x over L dx. Finally, bn is equal to 1 by L integral minus L till plus L f of x times sine n pi x over L times dx, where n can be equal to 1 to up till infinity. So we have got the Fourier series in terms of L by using a suitable scaling factor. So the transition from period 2 pi to period 2L is effected by a suitable change of scale. Now, considering f of x having a period p is equal to 2L, then we can introduce a new variable v such that the function f of x as a function of v has a period 2 pi. And this is done if we set x is equal to p by 2 pi times v. If we set our x is equal to p by 2 pi times v, and in this equation, we will easily get the form shown over here. So essentially, we have changed from period 2 pi to any period 2L. And this generic equation will be used in our structure mechanics. The form of Fourier series which we have discussed so far is called the long form. We can also reduce our Fourier series in short forms. So instead of taking both the cosine and sine terms, we can also take cosine term or sine term. This is a simplification done for the ease of our calculation. So before discussing this type of simplification, we have to remind ourselves of two types of functions, one called as even function and another one called as a odd function. An even function is a function in which if we put negative value, we will get a positive value. In other words, the even function looks something like this. So if we put negative value of x in this function, we will always get a positive value, as we can see. So this function is a mirror image of itself, and this function keeps on repeating at equal interval. If our unknown function is an even function, then we can reduce or simplify our Fourier series into f of x equal to a naught plus summation n is equal to 1 till infinity an cos n pi x over L, where a naught is 1 by L integral 0 to L f of x dx, and an is equal to 2 by L integral 0 to L f of x cos n pi x over L dx, and n can be 1, 2 till infinity. Thus, in the case of even function, we can eliminate the sine term of our Fourier series. And also, we can just take half of our period, which is 0 to L, and we will capture the whole function. Similarly, if we have a odd function where f of minus x is equal to minus f of x, as we can see over here. So if we put f of minus x, we get minus f of x. Then we can simply write our function f of x equal to bn sine n pi x over L, where n is from 1 till infinity. So in the case of odd function, we have only the sine term, and bn can be found equal to 2 by L integral 0 to L f of x sine n pi x over L dx. So we have essentially discussed three different forms of our Fourier series. The first form is considering both cosine and sine term. The second form is considering only cosine term and is applicable to even functions. And the third form is considering only sine term and is applicable to odd functions. If our applied law is either an even or odd function, then that will simplify our calculation and we will be able to approximate a function using these half-range Fourier series. So imagine if we have a rectangular wave, which is shown over here. This is a rectangular wave, which is repeating itself after interval 2. So the wave is given to us over here. We have f of x equal to 0 if when x ranges between -2 and -1, f of x is equal to k if x ranges between -1 and +1, and f of x is 0 if x ranges between 1 and 2. The overall period 2L is equal to 4, as we can see over here, and L is equal to 2. So we can solve this problem by using our full form of Fourier series. So first of all, we have to work out our baseline constant a naught, which is equal to 1 by 2L minus integral minus L till plus L f of x dx. Since L in this case is equal to 2, we can plug the values in this integral and we can get our a naught equal to k by 2. Similarly, we can find out our an by using this equation. and an comes out to be 2k by n pi sine n pi by 2. In a similar manner, we can find out our bn, and we can write our equation f of x equal to k by 2 plus 2k by pi, small bracket, cos pi by 2x minus 1 by 3 cos 3 pi x by 2 plus 1 by 5 cos 5 pi x by 2, and so on and so forth. Instead of finding bn, we can see right from the get-go that this is an even function. And in case of even function, bn is equal to 0. So plugging the values in bn, we can verify that bn comes out to be 0. Or we can use half-range cosine function and approximate our function into the cosine function. Now this is another example where we have a function value equal to minus k when x is between minus pi and 0, and f of x is equal to k when x is between 0 and pi. The function is given to us over here. Since the period of this function is 2 pi, therefore it would make sense to use the Fourier series in terms of period 2 pi. So between minus pi and plus pi, we have got the function value equal to k between 0 and pi, and equal to minus k between 0 and minus pi. From Fourier series, we get our function equal to 4k by pi, small bracket, sine x plus 1 by 3 sine 3x plus 1 by 5 sine 5x. So we can find the partial sums of this function just to appreciate that how many sums are essential to approximate the whole function. So the first partial sum is equal to 4k by pi sine x. The second partial sum, S2, will be equal to the first two terms of the Fourier series. Similarly, S3 will be the first three terms of the Fourier series. So our actual function is shown over here in black, and the term S1 is shown as a sine wave. So this is a very crude approximation. The first partial sum S1 gives us a crude approximation. The second partial sum is shown in blue over here, and that clearly shows the function is now trying to tailor itself to the given function. The third partial sum seems to be coming even closer to the actual function. Thus, as we keep on increasing the terms of our Fourier series, we are actually converging to the actual function. The main idea in Fourier series is to find out the minimum number of terms that will give us a reasonable approximation to the function. Obviously, in this example, just taking the first term is a very crude approximation to the actual function. So convergence is an important criteria in the case of Fourier series. Now we consider a function f of x is equal to x minus x square and check which of the three Fourier series will give us the fastest convergence. So the Fourier series containing cosine, Fourier series containing sine, and Fourier series containing both cosine and sine will be worked out. So the first step is to draw this function. This function will look something like this one. We are asked to find a Fourier series containing cosine terms only. As we discussed, the Fourier series having cosine term will be able to approximate even functions. Thus, in the case of this function, we can assume that we have got a series of these functions at the left and right of the x-axis. We will use now f of x is equal to a naught summation n is equal to 1 till infinity a n cos n pi x over L and work out our a n. So a naught is found equal to 1 by p 0 to p f of x dx. We can call it p or we can call it L. It's up to us. But the range is 0 till 1. So we plug the values in this and we find a naught equal to 1 by 6. Similarly, we find out an, which is 2 by p integral from 0 till p f of x cos n pi x over p dx, plugging the values, and we get an is equal to minus 2 by n square pi square small bracket 1 plus cos n pi. So if n is odd number, that tells us an is equal to 0, and if n is even number, then an is equal to minus 4 by n square pi square. Thus our f of x is approximated as 1 by 6 minus 4 by pi square big bracket cos 2 pi x by 4 plus cos 4 pi x by 16 plus cos 6 pi x by 36 plus cos 8 pi x by 64 and plus so on and so forth. In the second part, we are asked to find out Fourier series containing sine terms only. Thus, we will make use of the sine Fourier series, work out our Bn first, and then find the approximate function f of x. Function f of x will come out to be 8 by pi cube, big bracket, sine pi x over 1 plus sine 3 pi x over 27 plus sine 5 pi x over 125 plus sine 7 pi x over 343 plus and so on and so forth. Similarly, in the third case, we are asked to find both sine and cosine terms, and we get f of x equal to minus 1 by 3 plus 4 by pi square, big bracket, cos pi x over 1 minus cos 2 pi x over 4 plus cos 3 pi x over 9 minus cos 4 pi x over 16 plus so on and so forth, and plus 2 by pi, big bracket, sine pi x over 1 minus sine 2 pi x over 2 plus sine 3 pi x over 3 minus sine 4 pi x over 4 and so on and so forth. So these are the three approximating functions. The first one is in a form of cosine, the second one in the sine form, and the third function in both cosine and sine form. The reason we have worked out three Fourier series is to find out that what will be the best choice considering the ease of computing the Fourier coefficients and the speed of convergence of the resulting series. In the case of this first cosine series, we see that these terms are reducing by the power n power 2. We have this term getting divided by 2 power 2, then 4 power 2, then 6 power 2, and so on and so forth. In the case of sine series, we see that we have these terms getting divided by n power 3, i.e. 1 power 3, 3 power 3, 4 power 3, and so on and so forth. In the case of third Fourier series, we see that it is getting divided simply by n power 1. This clearly tells us that for the given function, the sine Fourier series convergence is fastest. After that, the cosine series convergence is faster. The Fourier series is the slowest of all three in convergence. So this is an important understanding of different types of Fourier series. We will now discuss solution of two-dimensional problems in the form of a Fourier series. This discussion is in the continuation of plane stress problems. We will try to employ stress formulation. The previous two examples of simply supported beam and a fixed-ended beam were solved using polynomial functions. Polynomial functions are good at handling those loads which are uniform or which are continuous. However, if we have a complex set of loading, especially a discontinuous type of loading, then the rate of convergence of Fourier series is very high as compared to the polynomial function. Let us see how the stress functions can be derived in terms of trigonometric functions. So this is our compatibility equation written in terms of x and y. It is partial 4 phi by partial x4 plus 2 times partial 4 phi by partial x square partial y square plus partial 4 phi by partial y4 equal to 0. This equation is considering that body forces are 0. So we define our stress function equal to sine m pi x over L times Fy. Thus, we have separated our terms into x and y, and both terms are getting multiplied with each other. As we know from our previous discussion, that by separating our variables in this fashion will help us get ordinary differential equations in the end. This function sine m pi x over L is analogous to half-range sine Fourier series. We are taking only one term of our half-range sine series and we are considering the weighted factor equal to 1. In the case of half-range sine series, we are dealing with only half period of the function. Thus, we are integrating our function between 0 and L. We can call m pi over L as alpha and plug the values in the compatibility equation. Thus, we will get equation alpha 4 f of y minus 2 alpha square f double dash y plus f4 y equal to 0. This is a characteristic equation, and from this equation we can get our function f of y equal to c1 cos hyperbolic alpha y plus c2 sine hyperbolic alpha y plus c3 y times cos hyperbolic alpha y plus c4 y times sine hyperbolic alpha y. We can plug the values of fy in our phi equation and we will get phi is equal to sine alpha x times small bracket c1 cos hyperbolic alpha y plus c2 sine hyperbolic alpha y plus c3 y cos hyperbolic alpha y plus c4 y sine hyperbolic alpha y. After finding out phi, we can use Airy stress function to get our sigma x, sigma y, and tau xy. In this example, we are using xy coordinate system rather than x1, x2. Thus, sigma x comes out to be sine alpha x, big bracket, c1 alpha square cos hyperbolic alpha y plus c2 alpha square sine hyperbolic alpha y plus c3 alpha times small bracket 2 sine hyperbolic alpha y plus alpha y cos hyperbolic alpha y plus c4 alpha times small bracket 2 times cos hyperbolic alpha y plus alpha y sine hyperbolic alpha y. Sigma y comes out to be minus alpha square sine alpha x small bracket c1 cos hyperbolic alpha y plus c2 sine hyperbolic alpha y plus c3y cos hyperbolic alpha y plus c4y sine hyperbolic alpha y. Similarly, tau xy comes out to be minus alpha cos alpha x times c1 alpha sine hyperbolic alpha y plus c2 alpha cos hyperbolic alpha y plus c3 small bracket cos hyperbolic alpha y plus alpha y sine hyperbolic alpha y plus c4 small bracket sine hyperbolic alpha y plus alpha y cos hyperbolic alpha y. After finding out the stress components, now we can use the boundary condition to get our constants C1, C2, C3, and C4. So, for example, consider a case where we have load in the form of sine wave applied at the top and bottom of the wall. We have a coordinate system xy shown in this figure. The origin is starting from the left side of the wall. The distributed load can be written as A sine alpha x at the top and B sine alpha x at the bottom, where alpha is equal to 4 pi by L. A and B is the amplitude of sine wave at the top and bottom of the wall. Alpha will be equal to 4 pi by L. Since we have two full sine waves, therefore we can write alpha times L is equal to 4 pi. And from there, we will get alpha is equal to 4 pi by L. Now, we can apply the boundary conditions and get our constants. So the first boundary condition is that at y is equal to plus c, tau xy is equal to 0. Thus, there is no shade at y is equal to plus c, and sigma y is equal to minus b sine alpha x. The reason sigma y is taken minus is because during the first half of the sine wave, we have got compression, and according to our convention, tension is considered positive. Similar argument apply at y is equal to minus c, i.e. we have tau xy equal to 0 and sigma y equal to minus a sine alpha x. Now these values can be substituted in this equation. We can get c3 equal to minus c2 times alpha cos hyperbolic alpha c divided by cos hyperbolic alpha c plus alpha c sine hyperbolic alpha c, and c4 equal to minus c1 alpha sine hyperbolic alpha c divided by sine hyperbolic alpha c plus alpha c cos hyperbolic alpha c. Now we can write this second condition, which is sigma y is equal to minus b sine alpha x and sigma y is equal to minus a sine alpha x. And the four constants comes out to be c1 equal to a plus b by alpha squared times sine hyperbolic alpha c plus alpha c cos hyperbolic alpha c divided by sine hyperbolic 2 alpha c plus 2 alpha c. c2 comes out to be equal to minus a minus b by alpha square cos hyperbolic alpha c plus alpha c sine hyperbolic alpha c divided by sine hyperbolic 2 alpha c minus 2 alpha c. c3 comes out to be minus a minus b by alpha square alpha cos hyperbolic alpha c divided by sine hyperbolic 2 alpha c minus 2 alpha c. c4 is equal to minus a plus b by alpha square times alpha sine hyperbolic alpha c divided by sine hyperbolic 2 alpha c plus 2 alpha c. These can be substituted into our sigma x, sigma y, and tau xy, and we get the final form of the three equations. Now we have worked out all the constants, and all the stresses can easily be worked out by plugging the constants in our stress equations. So instead of this type of function, we can have any other type of function which can easily be accommodated by our stress function. So imagine if we have a function at the top and bottom in the form shown. In this case, we have to convert the top and bottom loads into Fourier series. Once these are converted into Fourier series, then we can get our boundary condition in a similar manner to the sine wave problem. We can also find out our stresses if we have a pointed load. In the case of pointed load also, we can convert it into an equivalent UDL patch load, and after that use Fourier series to approximate this load and get the values of our stresses. Thus we can see that Fourier series can be employed to approximate different types of loadings. Imagine we have a problem shown over here in which we are given loads on a bunker wall. We have got a load per unit area applied along the length L at the top of the bunker and a patch load at the bottom of the bunker. We are asked to carry out stress analysis of this problem. So this is similar problem to what we discussed over here. We have already worked out the stresses in the form of constants C1, C2, C3 and C4. All we have to do in this case is to convert these loads into Fourier series and then use the boundary condition to get our final stresses. So this will be similar to what we have over here. We have got a load, and this load at the top, both at the top and bottom, can be converted into a Fourier series. And then we can use this approximate function to get our boundary conditions and finally determine our constants. So this load, which is a patch load, can be approximated into Fourier cosine series. As we can see, this is a even function. In this case, we have the overall period between 0 and L. So we can take just half length of this wall as half period. We can work out our constants and get an approximate function for the patch load. We can carry out similar exercise for the top load, and after that use the boundary conditions by considering sigma y equal to the Fourier series which we would have derived. We would have 4 equations and 4 unknowns in terms of C1, C2, C3 and C4. They can be worked out. Then the constants can be plugged back into our airy stress functions and we can get the stresses in the system. In a similar manner, we can have a beam which has got a cosine load. So this is also a similar problem to this one. So instead of a continuous sine wave, now we have a single cosine wave having a period 0 till L. Surely this can be solved using the cosine Fourier series. So the amplitude is P1 and alpha will be equal to pi by L. The half period will be equal to 0 to L. As we discussed, we can have f of y worked out in terms of cosine and sine hyperbolic trigonometric functions. We can have our airy stress functions worked out. After that, we can plug the boundary condition. The boundary condition this time would be at y equal to plus c, tau xy equal to 0, and sigma y is equal to minus q time cos alpha x, where q is taken equal to P1. At y is equal to minus c, we can take tau xy equal to 0 and sigma y equal to 0. Noting that in this case, we are taking x-axis in the horizontal direction and y-axis vertically up. Therefore, sigma y is equal to 0 at the lower boundary. As we can see, there is no load applied at the lower boundary. 4 equations and 4 unknown will give us constants C1, C2, C3 and C4. We'll plug back these constants in the airy stress function and work out our stresses. In part 2 of this question, we are asked to show that when we apply similar load at the bottom, then two of the constants of integration would come out to be 0. And let us see how we get 2 of our constants equal to 0. If we place another load at the bottom, which is opposing the top load, that would mean the fiber associated with the x-axis will remain straight. Thus, we can say that any quantity varying along y must be an even function with respect to x-axis. In other words, fy must be an even function. Thus, from symmetry, we can say that fy must be an even function. So, all the terms which are odd in our fy function will have to be 0. C1 cos hyperbolic alpha y is an even function. C2 sine hyperbolic alpha y individually is an odd function. C3 y cos hyperbolic alpha y is an odd function. And C4 sine hyperbolic alpha y is again an even function. Thus, we can say that the term 2 and term 3 must be 0 because they are odd function. Thus, C2 and C3 must be equal to 0 by inspection. So Fy will be equal to C1 cos hyperbolic alpha y plus C4 sine hyperbolic alpha y. Hence, by symmetry, we will eliminate the two constants.